Okay, here we are with part 2 of our Unit 3 practice test. Number 9 here, question. Investigate the piecewise function g of x, represented by x squared when x is less than 0 or equal to, 5 when x is between 0 and 2, and 3 when x is greater than, between 2 and 6. First step here says letter A, to investigate a function means complete the following table of values along with an accurate sketch of the function. So, table of values, you can all manage that, I believe. But when x is less than 0, so we're looking at like, -3, -2, -1, 0. So 0 squared is 0, -1 squared is 1, 4, and 9. So it's equal to, so I have a closed circle there. All right. And everybody here can graph half a parabola. That's what it would look like. No shifts or nothing involved. Okay, that's first piece. Second piece, g of x equals 5. That means y equals 5. That's a horizontal line between 0, not including, and 2. So I'm going to have an open circle here, okay, and then a closed circle at 2. All right, and a horizontal line. Okay, and then last one there, 3 between 2 and 6, not including 2. Okay, so that means now I'm going to have a horizontal line from here until 6, and it'll be a closed circle there. And a horizontal line connecting. Okay, so we have part of this is like a step function. The other part here is a parabola. Now, parent family name is piecewise, okay, because it's made up of multiple families. All right, x and y intercepts. Well, it looks to me like we have an x-intercept here at 0, 0. All right, and we also have a y-intercept at 0, 0. Now, some people might say we have a y-intercept here at 0, 5. However, that's an open circle, which means that actual coordinate doesn't count. Okay, domain and range. Domain is all possible x values, which in this case are -infinity. Whoops, didn't want to do that. X equal to 6. That's where our domain ends. And we can get that from here. Okay, look, everything less than 0, and it stops at 6 with a closed circle. Okay. In between, we're covered. Okay, at 0, we have this point. At 2, we have this point. So even though we do have some holes in the graph, those points are still covered by filled-in circles. All right, what about the range? The range of this function. The lowest it goes is 0, and it does actually touch 0. Okay, the highest it goes is infinity. All right, now I realize we have some holes over here. That's fine, but this part of the piecewise function overlaps all of those. Okay, vertex, if any, that would be where the place where the slope changed from positive to negative. I know if this parabola continued here, this will be a vertex, but at this particular point, there's no vertex. Asymptotes, none. There's no values that the graph approaches and doesn't actually touch. Okay, maximums and minimums. Maximum here would be infinity, but that's not a coordinate, so we're not going to record that one. Minimum here would be 0, 0. Okay, so that's what an investigation of a piecewise function would look like. All right, moving on. Let's take a look at the next problem here. Consider the function 2x squared minus 1 between 2 and 4. Estimate the area under the curve using 4 left-hand endpoints and rectangles. All right, so if we're going to do that, first of all, between 4 and 2, we got to figure out the width. So 4 minus 2 is 2. Divide that by 4 rectangles, okay, and we get 0.5 equals our width. All right, so we're going to start at 2, and we're going to count by 0.5. 2.5, 3, 3.5, 4. Okay, and then we're going to plot our graph. Okay, so let's see here. 2 squared is 4, times 2 is 8, minus 1 is 9. So we got to get to 9 here. So we're going to have to count by 2's probably. So that's 10. So that means 9 is going to be right here. Okay, and then let's see here. 3 squared is 9, times 2 is 18, minus 1 is... Okay, we're going to have to get a lot farther than that. Sorry about that. Let's see here. Let's count by, let's see here. 4 squared is 16, times 2 is 32, minus 1 is 31. So we got to get to 31. Sorry, 1, 2, 3, 4, 5, 6. So we count by 5s, okay? So 5, 10, 15, 20, 25, 30. Okay, so 4 is 31. All right, we said 2 was 9. 3 squared is 9 times 2 is 18 minus 1 is 17. So it's right about in the middle here. All right, so it kind of looks like a parabola there. We're talking about left rectangles. And drawing our rectangles. That means the left side of the rectangle is going to be touching the line. Doesn't matter above or below. Shade the area that we're going to be finding. Okay. Widths are 0.5. Is your estimate an upper or lower bound? It's going to be a lower bound. We can answer that now. Now this isn't asking for it, okay, but if we actually wanted to determine this, we would have to use sigma notation. So if I write this in sigma notation again, I write the original equation, I leave an empty set of parentheses where the variable is, okay? Inside of those parentheses, I write a little mini equation for how my x values are changing. Okay, my x values are changing by 0.5. Okay, and they start at 2. All right, and I'm using left rectangles. Left always begins at 0 and goes to 1 less than the number of rectangles, in this case 3. And I got to remember to multiply by my width. Okay, and then that sigma notation there would give me the area under the curve for this particular problem. So what would that area be? So once I add up all those y values and multiply by 0.5, the area here ends up being 29.5 units squared. To improve your estimates and still use left-hand endpoint rectangles. That means you just have to have more rectangles. Okay, how many? I don't know, 1 million. Okay, we have to have so many that the widths of those rectangles are basically straight lines. Okay, so the width is that small that there almost is no width. Okay, it would be the limit as it approaches 0. Okay, all right, then moving on here. Let's see, some laws of logarithms. All right, it's always a good topic, okay, to know here. So laws of logarithms: simplify each expression and solve if possible. So here, these logs don't have a defined base, so we'll assume the base is 10. And if we're adding those logs together, that means we can multiply. 5 times 2 is 10. Log base 10 of 10, so 10 to what power gives you 10 is 1. All right, here we go. We have same bases, okay, with subtraction. That means we can divide those logarithms. So log base 3 of 9 over 1/27. Well, we don't want to have a fraction inside of a fraction, so we should multiply by the reciprocal. So log base 3 of whatever 9 times 27 is, it's going to be 243. All right, and then 3 to what power equals 243. All right, and then that's what you would do to figure that out. Or you could always do your change of base, log of 243 divided by the log of 3. Either is fine, but that equals 5. All right, here we have a couple things going on. We have log base 3, log base 3. We have 4 squared, which is 16, and 2. So we can combine those, log base 3 of 16 times 2, which is 32. Can we solve that? 3 to a particular power equals 32. It wouldn't be a whole numbered power. We would get a decimal answer. So we could always do log of 32 divided by the log of 3. That's our change of base rule. And determine whether or not we know that answer. It would be a decimal answer. Okay, so still possible though. And we end up getting 3.155. Then the last one here we have, let's see here, we have log base 2 of 16, log base 5 of 25. Well, we can't combine those using any of our laws of logarithms, but I can simplify log base 2 of 16. 2 to what power gives you 16? 4, good answer. And then I can simplify log base 5 of 25. 5 to what power gives you 25? Squared. 4 plus 2 is 6. Okay, so there's always typically a way to be able to determine what these are, just not always the same method. Next, number 12. Write each problem in the form y y equals a times b to the x form. It does have a plus k there. I don't know if any of these have a plus k with them though. So let's see here what this is going to look like. These are some good problems. Oh, converting radians to degrees. That's good. That's a good review from chapter 1 that some of us still struggle with. First, let's start here, okay? We want a times b to the x. Right now we have a times b to the x minus 2. Because this is minus, we can separate that exponent into 2. So we'll have 32 times 2 to the x divided by 2 squared. You don't need the negative. The minus sign turns into division, okay? So what is 2 squared? 2 squared is 4. And then what we're looking at there is 32 times 4 can be simplified. Or excuse me, 32 divided by 4 can be simplified, and that will be 8 times 2 to the x. All right. Letter B, we have 1/27 times 3 to the x plus 5. Again, this is addition. That means that can be separated using multiplication. So 1/27 times 3 to the x times 3 to the 5th. All right, well, 3 to the 5th we just did in the last problem is 243. So now we can do 243 times 1/27. So basically 243 divided by 27. All right, and that simplifies to just plain old 9 times 3 to the x. Okay, so again, division, we can separate that using, or excuse me, subtraction, we can separate using division. Multiplication, you can separate using, addition, you can separate using multiplication. Here we have division. We have no a value out in front. That's okay. So we have 4 to the 2x. All right. Whoops, let me start over here. We have 4 to the 2x divided by 4 to the first. Well, dividing by 4 to the first is just like saying 1/4. So if we want it in a times b to the x, we need to write 1/4 times 4 to the 2x. And now we still don't have a times b to the x. We have a times b to the 2x. Okay, so to simplify that, we want to actually figure out what is 4 squared. So we have 1/4 times 16 to the x. Convert from degrees to radians or vice versa. Again, the proportion I would like you to use is d over 180 equals pi, or excuse me, equals r over pi. Okay, Mr. Warner would help if I gave you the right one. All right, so r over pi. And you plug in what you know. Look, degrees, if that's what we're looking for, decimals are okay. Degree, decimal. Radians, if it's radians we're looking for, we just want to reduce. All right, we don't want decimals. Here we're looking for radians. We have degrees. So we're going to plug in a 128 over 180 equals r over pi. Now, if you can simplify right away, I'm okay with that. 128 and 180 are definitely reduced. I mean, you can reduce those by 2 for sure, okay, which would give you 64 and 90. So 64 over 90 equals r over pi. And that might make your work a little easier. Let me cross multiply. So we end up with 64 pi equals 90r. Do not multiply 64 times pi in your calculator. We don't want a decimal there. Okay? Then we divide by 90. They cancel out. So radians equals 64 pi over 90. Now we just have to determine, can that be reduced? Does 64 over 90 reduce, okay, to a simpler fraction? And you can use your calculator to do that, people. You don't have to necessarily, think about it, do it by hand. All right, but in this particular case, they're both, again, divisible by 2, which means best answer here is going to be 32 pi over 45. And we would prefer that for now over decimals. Okay? Now I'm going to erase that to do the next one here because I need some room to write. All right, so here we go, 5 pi over 8. So now we know radians, and we're looking for degrees. Now look, even though that's a fraction, I still plug it in inside of the fraction that I already have. So many people forget that. They forget this part right here. That denominator is pi no matter what. All right, cross multiply, so d pi equals 180 times 5 pi over 8. All right, now luckily for us here, we have a pi on both sides. They cancel. So now we have 180 times 5/8. And again, I don't care if you use your calculator for that, or you could reduce it by hand. It doesn't matter to me. So 180, okay, and then we end up with 112.5 degrees. And decimals are okay because we're talking about degrees. All right, moving on. Only one more problem it looks like here. Write the following using sigma notation. Ooh, that looks like a tough one. 2/3, 4/9, 8/27. Okay, it goes all the way up to 256. So the top looks like it's doubling. Okay, or it's 2 to the first, 2 to the second, 2 to the third. And the bottom, we have to write the bottom the same way using the same variable. It's a tough one there. Okay, so let's take a look at this. All right, this is going to throw us for a little bit of a loop here. This would be a good team test problem. I don't know if this one will be on the test. Take care of that first. Okay. Now, what we need to do is figure out an equation for the top. Now, you could say it's doubling each time. Okay, 2, 4, 8, and then it'll be 16, so on and so forth. So if that's the case, we're thinking about an exponential there. So 2 to the k power. All right. Now, the bottom's a little different, though. The bottom looks like 3 to the first, 3 to the second, 3 to the third, so on and so forth. Okay, but we need to be able to write that still with using k. Okay, so that's going to be 3 to the k power. All right, and k needs to begin at, in this particular case, k would begin at 1 because it's 2 to the first and 3 to the first. Okay, so k has to start at 1 here. All right, and then how far will it go? Well, 2 to what power gives you 256. All right. And that's going to end up being 2, excuse me, to the 8th. All right. And then you just got to check to make sure that works for 3. 3 to the 8th equals 6561. All right. So there you go. That's a tricky one. Hopefully you are prepared for the test tomorrow.